So now we will study diffusion networks, which are at the moment one of the most successful generative models. So let's start by defining diffusion. So diffusion is somehow can be seen as the evolution of some random variable. So let's say that we have the evolution in time of some random variable. So we will have a collection of random variables indexed by time, and a Markov process is a stochastic process. So a stochastic process is this collection of variables. So if this collection of variables is such that the given some observations of the process, and so the observation at time tn, so at the nth time, only depends on the previous one. So it does not depend on the whole history, but the whole history, the influence of the whole history is condensed in just the previous sample. So if this sequence of stochastic variables follow this property or fulfill this property, then it is a Markov process. So a diffusion process is a Markov process that satisfies some differential equation, a stochastic differential equation. So in this equation, how the variable changes at time t depends on what is the time step. So basically in this equation it is differential, but it depends on how far you are trying to predict into the future, and there is some drift plus some random sampling. So this random sampling is called this part is called the diffusion coefficient, that depends on the current time and the current state, and this is a standard Brownian motion. So it is another random variable that somehow fulfills this property. So the differential of the random variable follows a Gaussian distribution with zero mean and a variance that depends on the differential of time. And this differential of time, this differential of the noise is just the difference between two observations of that noise. So depending on how this is the standard Brownian motion, so depending on how far you go in time, the variance of that the variance of that observation is larger and larger. So yeah, this is the differential equation of the diffusion process. Now we discretize it. So the differential is this thing, and this is the differential in time, and then this one, that is somehow this is just a random variable coming from a Gaussian distribution. And now we can rearrange this part, that is, we take it to the other side, and then this u prime will be, so instead of having variance differential of t, it has variance sigma squared differential of t. So this is the forward diffusion. So the forward diffusion, the Brownian motion can be seen as a forward diffusion. So you start at a point and you diffuse that point, and that is where each one of these trajectories is where the point will end after whatever time. So now we can think of the reverse time process. So the reverse time process is the opposite. So in the forward diffusion, we start at a point, we let it go, and in the reverse time process, we just reverse the time axis. So we see x bar t, so it is just x of the final time minus t. So it is just reversing, so just making a flip, an horizontal flip of this process. Okay, and then there is also a differential equation that is a reverse time must fulfill. It is this one. So it is very similar to the previous one, but now there is something new, that is this score function. So the score function, this P of xt, is the marginal probability density distribution of xt. So it is the distribution at each time point. Okay, then diffusion, we are still with diffusion, not reverse diffusion. So diffusion destroys all information. So you start with a distribution of values, and this distribution of values, let them evolve through this differential equation, not differential, but kind of difference equation. So the observation at the next time will be square root of 0.99 x of t minus 1 plus square root of 0.001 ut, where ut is a random number. And then what it goes, it starts with whatever distribution, it will always go to a Gaussian 0-1 distribution. So it will be asymptotically transformed into a 1D Gaussian. So no matter what distribution you start, the information is completely destroyed. So this also happens with any kind of signal. So let's say that our process is this one. So the next image will be square root of 1 minus p, the previous one, plus square root of p, some random noise. So you start with this image, you corrupt it a little bit more, a little bit more, a little bit more, and at some point you are in a Gaussian 0-1, so of 0i. So going from a clean image to noise is extremely easy. So it is just to follow this procedure. Inverting the process is much harder, and no matter how the image looks like at the beginning, the information will be completely destroyed after many steps of this iteration. Okay, so now we know the forward process. Now we can try to invert the inverse process. So if we were almost at the end, it would be relatively easy. So given this image, we could try to get an idea of what the noise was, so that we can subtract it. And this is a little bit harder, but not so difficult. This is extremely difficult. So let's see how we can try to invert each one of these steps. So the generative model based on diffusion network, it will start with some random noise, and we'll try somehow to denoise it more and more until it has some properties that we are satisfied with. Okay, so the forward operator is f, that is fixed, and we know how to apply it multiple times. The opposite we have to learn, and actually we can think of there should be a single operator, that is the composition of all these operators, such that we can go directly from the last step to the first one. But so in principle, if we can learn the individual steps, we could also learn the global composition. The problem with the global composition is that it is much harder to learn. So as a function, it exists, but it is much harder to find what this function is. So moreover, because we can try to make all these inverter operators to be recovery operators to be the same. So it is just one operator that given the current image, the current state, and a step, will go back one step. Okay, so yeah, the message here is G star, that is the one that goes directly, would have many more parameters and would be much harder to learn. Okay, so we will try. So x0 is the initial image, and there is a distribution of x0, and then with our network we will try to learn to learn what is this distribution, and this distribution we will measure the distance with the divergence of KL divergence. Okay, so let's see how to do that. So there is a function, so how to approximate Q, so the distribution of xt minus 1 given xt. So we know how to do the forward. So the forward is very easy. So it is the distribution of xt is a Gaussian distribution whose mean is this one. So the square root of 1 minus beta t, and then here you have beta t as variance. So square root of 1 minus beta t times the current state. Okay. So yeah, so how to invert it? So this is given t minus 1, how to get t. This is given t, how to get t minus 1. So what we will do is we will approximate with some Gaussian, okay, and the Gaussian has to give a mean and a variance that have to be learned. So we will start with a 0i distribution, so a 0-1 distribution in multiple dimensions, and then for every step we have to learn this backward process that predicts what is the mean and what is the standard deviation. So during training, beta t is the variance of the noise to be added at each stage. So we can see it here. So beta t is the variance of the noise that has to be added at each time point, and this beta t has to be fixed in advance. So the scheduling of beta t has to be fixed. Okay, so then given the scheduling, we can compute AT, and this A bar t, that is the product of all the ATs, and then we can go directly from x0 to xt, so we don't have to go one by one, so we can go directly using these A bars. And okay, so during the training, what we will do is you take one sample from the initial data, so these are clean images, then you take some uniform time, then you take some random noise, and then you simulate what is the image at that point, and then you take the gradient descent of the gradient over your parameters of the true noise minus the noise predicted by the network. So the network has to predict what is the noise that was added to go from x0 to the current sample. So that is how it is trained. Okay, so here we have a graphical representation of that. So you take some sample image, some sample noise, you sample time step between 1 and t, and then you generate this random step from the random trajectory. So it is just going in one step from this x0 to xt. Xt in the middle between beginning and end. Okay, now the network takes this input image and it has some parameters and tries to estimate the noise in the noisy image, and then it tries to minimize the error between the true noise, this one, and the estimated noise. And then you update your parameters with respect to this loss function. So once you have converged, now how do we use this network? So this network, so you start with random noise, and then you will go step by step, and then at each one of those steps, the network has to predict what was the noise, and then it will construct an estimate of what x0 was starting from that estimate. And then we will update our mean. So the mean at that time is somehow it is a combination of what is xt and what is our estimated amount of noise. This beta and alpha, we said that they are pre-scheduled. They are pre-scheduled parameters. So we have a scheduling of how much noise we need to add, and we have this mean that we have it here plus some sigma, and sigma is coming from again from the scheduling times set. So times set. So it is, we are updating the mean and then we are adding a kind of noise before. Okay, then and we iterate this a lot of times until we reach x0, and then we return x0, that is the last one here. So here we have some examples. So let's start with a Gaussian noise. So this is for us our starting point, but it is the end of the diffusion process. So we have to invert the diffusion process. So we estimate from the model. So we have trained already the model. So we are now in generation time. So in generation time, we estimate what is the noise. So from this image, we estimate that the noise is this one, and then our estimated x0 is this one, and then from we estimate what is the next state, and the next state is a linear combination between the current state and the estimated x0 with some additional noise. That is the process we described here. Okay, then let's we apply a few iterations. Let's see how the middle iteration looks like. So this middle iteration, we are already here. We have to estimate what is the noise, and then we estimate what is x0, and then we estimate what is the next state again. And at the end, this is our current estimate of what the noise of the signal is, and then we estimate how much noise we have added, and we estimate x0 again as a linear combination, so as this formula here. Okay. And then we estimate what is the next one, and so on. So this is how we can go from noisy images to very clean images, trying to reverse every time a little bit of the noise that we have added. And sometimes this process can be very costly. So once you have converged and you know how to do it, then you can combine. You can do a kind of distillation of the process, so that instead of a complex model that is the teacher, that is the one we have just described, it is simplified by a student, and the student learns to achieve in one step what the teacher model does in two. So now instead of doing t steps of this process, you only need to do t over 2 steps, and you can process. You can put this idea forward with more steps. The other interesting idea is these consistent models. So these consistent models, somehow the forward process we understand very well. And in the backward process, so if we start with this image, we end up following the procedure we just described in this one. But if we start in this one, we also want to finish in the same, and if we start in this one, you also want to finish in the same. So this addition of random noise that we had in between of our recovery operator or the generation operator somehow has to be consistent. That is what this paper tried to solve. And actually the diffusion processes that we use are not just diffusion as such, but a stable diffusion. So a stable diffusion, somehow it has this kind of autoencoder architecture. And the autoencoder architecture, you start with, so in one direction it is just the diffusion process we described. So you have an autoencoder, so you have a vector, and this vector in the latent space, somehow it is diffused until noise. And then you have this noisy vector, and you go through the denoising steps. Each one of these denoising steps can take multiple information, and this multiple information is the previous state. And once we finish, we have the recover. We hope we have recovered this latent representation here, and then we only have to do a decoding. But also, this denoising can know something about the object you are trying to recover. So it is this conditioning that we also saw in the conditional autoencoders in the previous lecture. So here you can have semantic map, text, representation, images, whatever. So for instance, when we say generate an image of a dog, so the dog is text, and these denoising steps, they take information coming from the dog, so from the dog label, or generate an image of a dog playing football. So it gets all these texts, and this denoising is conditioned with this text. And if you are interested in these things, here I'm leaving more notebooks, so some notebooks and some explanations of the models. Here we have some very nice examples of how from these model inputs can produce this data, or from very blurred, so what is the prediction of the x0 for each one of these layers. So you see how x0 evolved from these ones that are just pure noise to the final numbers that it generated. Okay,